Okay, everyone, it's 11 o'clock. Let's get started. So I'm very excited for this panel that we are having right now on 3D modeling. The organization is going to be slightly different from some of the panels that we had yesterday. So just to give you an overview, the panelists have discussed extensively and have come up with 7 different topics that they think are interesting. So, and kind of one of the big questions is going to be, which of these should we delve into greater detail? So to start off, we're going to have short presentations by each of the 3 panelists. So Falk Herwig, University of Victoria, Ben Brown at CU Boulder, Pascale Garaud, who is joining us remotely from UC Santa Cruz. You can see her on the thing over there. She will be up on the main screen in a moment. But we're going to first start off with some presentations, short presentations by each of the panelists, giving kind of a broad overview, discussing some of these 7 topics. After that, we are going to switch over a bit. I'm going to ask everyone to discuss with their neighbors for about five minutes or so some of these questions, and then once that's done, I'm going to go over and call on random people and ask you what you were discussing. In addition, we also have a Google Doc set up. So if you go to ppmstar.org, click on this link that Falk is highlighting. There's a Google Doc. You can put some questions or comments on any of those 7 topics right there. And okay, so I'm not going to take any more of their time, but just overview again. Short presentations by the 3 panelists. Then a little group discussion. We're going to figure out what are the topics we want to dive into, and then we'll kind of revert to what we were doing yesterday and have more a discussion about those topics that we've identified. Okay, so with that, I don't want to take up any more of your time. Falk, why don't you get going? So I'm going to give you 10 minutes, and Matteo is setting the timer, so please go right ahead.
Yeah, so as Daniel was saying, the 3 of us discussed in 2 sessions, and we identified these 7 topics, and we got really started on the discussion and realized that we had slightly different takes on each of these sessions, each of these topics, and we thought it would be best to just each of us address them briefly, knowing that we can't sort of give a full, I mean, a lot of these are full presentations for an hour. We can't do that. We just touch on it and give you just our take on these different topics, and you get an idea of what the similarities and differences are, and then we can use that to start discuss. We thought that each of us starts with a brief introduction of what research questions we are interested in, each in our own way, so that you get an idea of what the different types of questions are that we are all in our own ways addressing with 3D Hydro. And so for our team, which is Paul Woodward's group, who's sitting right over there, and my own group at the University of Victoria, we're interested in nuclear astrophysics, stellar structure, dynamic, convective, reactive events in the late phases of stellar evolution. Examples are convective shell mergers. We're also now interested, and that's why we're, I think, at this conference also, is internal gravity wave properties and core convection in early evolutionary phases. And I put some examples in here. These are some of the simulations. This is a POP3 45 solar mass star with a helium burning shell. This is vorticity and a hydrogen, the bottom of the hydrogen burning shell, a little radiative layer between, pummeled full of internal gravity waves, and internal gravity waves here as well. And so this is just some examples. This is hydrogen ingestion into helium shell flash convection zone. This is the hydrogen rich abundance. The stuff burns here like crazy and produces all sorts of interesting time dependent convection things. This is oxygen shell burning with carbon. This is, I put this here for call. This is meant to produce supernova progenitors, aspherical supernova progenitors, and interesting nuclear synthesis. And these are sort of the internal gravity waves surrounding the core convection. This is a 2688 cubed simulation. So again, vorticity, the waves, and this is the type of interesting problems that we're interested in. Briefly, the methods. The methods are 3D hydrodynamic simulations in 4-pi sphere on dynamic timescales. And we also work on sort of reduced dimensionality post-processing approaches for large networks that could be maybe extended for 1D, 3D mapping. Okay, the second question is open questions. We felt each of us should address open questions that 3D models can possibly answer. And so this is just some things that are maybe possible, say in the next 2 to 3 years, realistically, so make that 5 years. For example, convective boundary mixing in specific situations we can do. There's an example of calibrating the F overshooting for oxygen shell burning in Jones et al. As an example, maybe for a massive main sequence star in the not too distant future. Time-dependent convection, these simulations that I showed you with a lot of energy feedback could be used to calibrate time-dependent convection models in 1D, understand nuclear predictions, internal gravity waves, and so the list is, I put the list up on the web page so you can look at it. 3D, 1D connection. Our vision here really is for 3D, 1D connection is, with Paul, we discussed over many years now some autocorrective 1D, 3D modeling approach to get us sort of connect the 3D the dynamic processes connected with the thermal timescale processes. The third topic are the 3D simulation approaches. In terms of Isabel's category, we do both idealized and sort of maybe realistic or almost realistic simulations. In Isabel's category, sorry, this. So we use the PPM star code that Paul has been developing over quite some time. It solves the envisaged compressible gas dynamics equations on a Cartesian grid with PPM and PBB for tracking, and sort of, I would say, towards realistic microphysics, and including sort of simplified burn networks and so on and so forth. So this is our 3D simulation approach, and others will report others. The code instruments. So in terms of code instruments, I would say what I would suggest is that we have to view building and maintaining code instruments. And you're all familiar, for example, with the MESA code instrument. There's other code instruments out there, the Flash code. But we should really view it as an activity similar to how we view observational instrument or telescope building and maintaining. I think that's a good framework, and we can discuss what that means and what the implications for that are. Just sort of I'm just briefly mentioning sort of ideas here. We have to discuss what the incentive models are for building codes. You get into questions like, yeah, well, I mean, this is something we can discuss, incentive models. I have some ideas about that. Importance of the integration of code experts into the science team. I'll just say that I have found myself writing a 10-page manuscript about something that we found in our simulations, and Paul was sort of cautioning me and saying, oh, wait a moment, and no, I have to say I could delete the entire manuscript. I have deleted it entirely. I worked like 3 or 4 days on it, and I could just toss it because Paul, because I had the luxury of having sort of really being very close to the code builder who really knows. So this is really important. We touched on this yesterday already a little bit in the context of observations, and people know what the pipelines look like. It's a similar thing like that, right? And it is really that you want to push the fidelity of the simulations, like you want to push the observations to the limit. And when you are at the limit, there are some instabilities. Okay, Which codes for which questions? 0.5 below. I thought that for the benefit of those of you who are not doing simulations all the time and 3D, I would briefly touch on my view of dimensionless numbers and why they matter. And I'm sure Ben and Pascale will give you a slightly different take. And they're all valid. They're just different views looking at the same elephant. So the conservation laws have a really amazing diversity of solution spaces, I would even say. There are sort of different solution spaces. And the dimensionless numbers allow us to navigate in this space. They tell us in which regime we are. And they also allow us to argue about it. And associated with that is this very powerful principle of dimensional similarity, which says if my dimensionless number are the same, or at least on the same side of unity, then and the topology of the flow is the same, then the answer has to be exact. I mean, it has to be the same, and that is just a really important statement. I'll just demonstrate it real quick. If we start maybe just as an example, and you can do that with all the processes, thermal and whatever you have, not included here. You start with the incompressible Navier-Stokes momentum equation. Here it is. Here's your viscosity and body forces and surface forces and all this stuff. And you make it dimensionless by picking some useful velocity and length scales and all this stuff, dynamic pressure here, to make it dimensionless. You end up with a dimensionless momentum equation. And what you find is that in front of these terms appear these ratios. And these ratios are the dimensionless numbers that we keep talking about. And for example, this here is 1 over the Reynolds number. This here is the Froude number squared, which is also the 1 over the Richardson number, and then there's the Struhal number. But the key point is that now we can say, let's say, for example, if the Reynolds number is very, very large, like it is in stars, well, then 1 over RE is very, very small. And that means that this term, generally speaking, doesn't matter in the momentum equation. And so that's why we then can say, well, let's just forget about it, right? So this is, but the other important point is that if we have sort of the same coefficients in front of these terms and we solve it, it should be the same answer. I'm so glad there's only verification validation left.
Folks, yeah, sorry, we want to make sure that we have lots of time for audience discussion.
I will just read the headers, and this takes 30 seconds, okay? Can I do that? And I'll not talk about, just read the headers because...
Okay, read the headers, and then...
The headers are verification, validation, and we can discuss more. Do I solve the right do I solve the equations right, and do I solve the right equations? These are, I think, really, really important to keep in mind. And I think I'm sure that we're going to talk about the 3D hydro community interactions 1D, 3D, and so here's some ideas, and I'll just close with that.
Great, thanks, Falk. Ben, do you want to set things up? Yeah.
Okay. I'm Ben, so I'm going to be our second short presenter, and then Pascale will be our third. Start the timer. Part of why we're doing this, part of why we're talking about what we do and the kinds of problems we work on, is that when we were visiting as a 3 group about how to do this discussion panel, we realized all the spots where we had things where we thought things mattered a whole bunch, and they don't matter for the other person's problem. So with Falk and me in particular, both working in global geometries, I have a thing I really care about, which is usually utterly irrelevant for the problems Falk is working on, which is equilibrium. Because I'm going to tell you a very brief bit about modeling stars on the main sequence in global geometries. And these are really problems of sort of quasi-equilibrium processes, sort of slow processes around a background, rather than very rapid processes that are changing the background continuously all the time. So getting the background correct matters a lot. Getting the equilibrium around that background correct matters a lot. This was such a big deal. It led to huge discussions in the last Stellar Hydro Days conference in Exeter, and led to Evan Anders writing a detailed paper on thermal equilibrium and like why why it's hard and why it matters, which it only matters for these kinds of problems, but not for Falk's kinds of problems. So here's my take on the 7 questions. So we're going to talk briefly about global models and the main sequence, some open questions, some approaches, some instruments, and dimensionless numbers, verification, 3D hydro. Pascal is going to do localized models of processes to wrap this off. So you see how these all tie together. Okay, so why global models, and how is the main sequence different in some sort of way? So for global models, a lot of the observables that we're interested in and a lot of the questions we ask about stars are questions that have to do with geometry or interactions with structure. So geometry, we often care about things like, hey, what's the large-scale dipole field of a star for magnetic braking? What are the mean flows that are established inside the star? And structure interactions, what happens when convection interacts with something like a penetrative layer, a tachocline of a star? How much mixing is there across it? These are all questions that either have to be in box geometries that are non-constant coefficient and have big changes, or global geometries where things change in latitude as well as in radius. Rotation, for example, is different at the poles of a star than an equator, and so you kind of need spherical geometries if you want to see the effect of rotation across the different parts of a star, at least for some problems. A lot of the problems of main sequence stars are quasi-equilibrium, and generally they're very numerically stiff. So what do I mean like this? Well, you've got some time scale, the evolution of the star, that's like giga-years. You have some time scale that your science happens on. Maybe you're interested in like solar cycles. That's like decades. Okay. You have some time scale that's your equilibration time of your simulation, the time scale for your simulation to get to a spot where it's actually modeling the thing you think that you're modeling. The time scale for that depends. I was generous and I made my science time scale outer to the equilibration time scale. Sometimes these two swap, and that's its own huge problem. And then you have some kind of dynamics you have to resolve, like convection in the sun, that's days, minutes, hours. And then you have a time scale of stuff you really don't care about. This could be, say, sound waves in the deep interior of the sun at low Mach number convection that's like whipping around on time scales of seconds while you're trying to integrate for decades, right? So this is a numerically stiff problem, and you have very short time scales, kind of medium time scales, and this is a real stiffness too. Okay. A lot of the questions for the main sequence are driven by statistics, like what's the transport and mixing of something, what are the characteristic shapes and amplitudes of something, like the magnetic fields. And so your accuracy matters a lot, and it matters that you are getting these statistics around an equilibrated state, because if you're getting statistics around a state that's still drifting, then your statistics may not actually be the right statistics of the physics you want to study. All right. What are some of the questions I think that are answerable in the near term with 3D global models? I think there are some things we could really say about the large-scale global flows, the differential rotation, and the meridional circulation of stars. We can't test in these models necessarily what those flows do, but we can give you an idea of what those flows might look like, and they could be tested with other ideas. And we've already seen interesting things like different stars have very similar differential rotations when they are in the same dimensionless parameter space. And those differential rotations can change a lot when you change the parameter space. So this picture is opposite in color to those pictures, and those pictures are all the same, even the little tiny M dwarf, which just has a different color bar because progress. I think another thing that's an answerable question is a question of what are characteristic magnetic field morphologies out of dynamo simulations. This is a very hard problem to answer in a consistent way that has any power for prediction into the real world. And I can say more about that later. Mateo, how many minutes do I have? Halfway, okay. To give you an idea of some of the dimensionless numbers we tend to talk about, I've written a few up here, and I've split the ones on the left from the ones on the right. The ones on the right are inputs, the ones on the left are outputs. The ones on the left are the ones we actually care about. We care about things like, what's the Reynolds number in all of its different flavors, magnetic, chemical, momentum. And this is something about how unimportant is this small scale effect that Falk was pointing out is small in stars and we should neglect. But it also ties into questions like how much does turbulence transport and affect things? And things change tremendously as you walk through Reynolds number space from values of 1 to 100 to 10 to the 4, and stars are at like 10 to the 12. So we see big changes in regime behavior as we make small changes in this sort of parameter, and we know stars are much further out still. Another interesting parameter for rotating stars is the Rossby number, which is asking a question of how much do the motions care about rotation? Do the motions in the star know that they're in a rotating body or not? There's some number that I labeled the does the sim matter number, and it's something about like, hey, what's your equilibration timescale compared to your dynamical timescale? And it ties into things like the Reynolds number and into questions like, have you run a simulation for long enough to be useful, and all sorts of other things. These three parameters on the left all change as functions of the parameters on the right. The parameters on the right are kind of classic input parameters. They measure things like diffusion versus buoyancy for the Rayleigh number, diffusion versus rotation for the Ekman number, and I threw some Prandtl numbers up there too. In stars like the sun, these Rayleigh numbers are like 10 to the huge. They're like 10 to the 28, 24, numbers like that. The Ekman numbers, 10 to the small. It's like 10 to the minus 15. And simulations can reach a fraction of that parameter space. Our best work is at Rayleigh numbers of, what, Lydia, 10 to the 6, 10 to the 8 for spheres, and Ekman numbers of like 10 to the minus 5. So we're like 10 orders of magnitude apart, or 20 orders of magnitude apart in the parameter spaces for each of these, from where stars actually are. And Pascale will show you some reasons why that matters in a few moments. It may actually be that these parameters are not the right ones and that some recombinations of them are the ones that actually govern the things on the left. We don't, in general, know how the knobs on the right, the things we set, result in the values on the left, the things we care about, though there's been a lot of progress in that. Other things, so we're talking a bit about approaches and things like that. There are a lot of different equations that get solved to try and capture the stiffness in the system and to eliminate things like the sound waves. These are choices of approximation, and there are different approaches for doing this, and here's sort of a hierarchy of these. This is much like Isabel was talking about this morning when she was talking about the anelastic tools and the what we call the pseudo-incompressible tools, ranging all the way up to the fully compressible tools. So there are different approaches solve different things. For the tools to solve these, there are a number of both open source and closed source tools in a variety of geometries. A lot of them tend to be spectral and high order codes because we care a lot about the accuracy of these solutions. And so a lot of effort has been put in historically on the Dynamo side in developing global spectral tools. ASH was a well-known one for a long time. The Rayleigh codes, the open source successor to that, there's the Magic code, there's the Pencil code out of Nordita, XShell, some others. Sometimes, especially a bit more in the planetary side, you'll see global circulation models brought into the stellar modeling place. Okay, and then there's music.
Okay, Ben.
I will finish in 1 sec. Some of us have done a different thing. It's fun. I want to leave with the verification and validation and then throw up the community things. Verification and validation is hard. There aren't usually analytic problems. There are not very many benchmark problems. Testing against other codes is very hard. And observations are tricky. So generally, you're doing things with internal convergence testing. I'll leave it there so we can switch to Pascale.
Great, thanks, Ben. Okay, Pascale, can you try to share your screen? Why don't you get started? We're going to give 10 minutes from Matteo, and you might not be able to hear it, but when it goes off, I'll let you know. So go right ahead, Pascale.
Okay, so my approach and that of a lot of people in the field is to do what Isabel referred to as box and a star problems. And we basically address the problem of turbulent mixing in terms of transport by small-scale instabilities. And these small-scale instabilities are either ones that have to be small-scale to develop, and a good example of that are double diffusive instabilities, which require diffusivity, so they have to be small-scale. And so this is fingering, semi-convection, GSF instabilities, and diffusive shear instabilities. And then there's also instabilities where the physics of the problem dictate the existence of a preferred scale that is small compared with a star. And a salient example of that would be the baroclinic instability for rapidly rotating stars, which where the scale of the eddies is limited by the rotation. So what we do, and when I say we, it's everybody who does this kind of approach. We take a little box in the star. The box is often, but not always, triply periodic. It often, but not always, uses a Buckingham approximation. You can use, as Adrian showed us, a constant background temperature or a background composition gradient to drive some kind of buoyancy mixing. We can add a constant background shear to drive shear instabilities. We can add rotation and magnetic fields to these simulations. I wanted to give a note on the Buckingham approximation. It's an approximation that is formally valid when your box size here is much smaller than any kind of scale height of the system, so pressure scale height, temperature scale height, density scale height, and when the velocities are much smaller than the sound speed. So don't believe any results of our simulations if they're applied in places where this is not realized. But other than that, it's basically a Taylor expansion in the small coefficient that is basically the ratio of, say, box size to scale height. So there's nothing fishy about it. The questions we can answer, I think when done properly, these simulations can provide flux laws of the form, here the flux is a function of all the local conditions within the stars. And following on the discussion yesterday, these flux laws have no free parameters. It's a function of known quantities within the stars. And so we can get flux laws for composition, temperature, momentum, angular momentum. And if you include magnetic fields, you can also quantify dynamo action by these small scale instabilities if you're interested in that. And then you can mix and match processes and see what the effect of some processes are on the instabilities. So look at the effect of shear, for example, on fingering instability, or the effect of magnetic fields like Adrian did. So lots of combining processes once you understand the basic ones. So I would say that what has been done recently is to quantify mixing by fingering, convection, semi-convection, GSF instabilities, diffusive shear instabilities, and dynamo action by either stratified turbulence or generally small-scale turbulence. So these are all recent progress by various groups in the world. And usually so far without additional physical processes, although there's now tentative work on combining processes as well. But that's kind of where the field is going now, is combining processes. The approach we take is to you first run a suite of simulations to explore parameter space. You identify interesting regimes, you try and understand them, actually figuring out what makes them tick, find the range of applicability of these regimes, and then extrapolate to stars. And because that's a bit vague, I just want to illustrate it. So suppose you have only two input parameters, P1 and P2. And you run a set of DNS, and by eye or otherwise, you figure out that these red ones are classified into one group and these green ones are classified into another group. Then you work very, very hard to figure out what's special about each grouping. And usually you try to identify some kind of force balance or energy balance or some rationale for what you're seeing that is quantitative. And that rationale should also not explain what happens in the group, but also explain the boundary with the next group, because that's usually when that rationale breaks down. And then finding, and usually, by the way, there's an emergent parameter that describes what happens in one group and another group. So it's not input P1 and input P2, it would be a new parameter that describes what's going on. Now finding that rationale and identifying the correct emergent parameters is a dark art. That's really difficult. And sometimes you can do it, you can work on it for a year and you still can't figure it out. And other times it just happens and everything comes together and you have your explanation. But there's no one approach fits all to understand these regimes individually. But once you have that, right, you have these emergent parameters and you can figure out what the fluxes are as a function of both emergent and input parameters. So you have these laws. And these are laws that are numerically validated in this region of parameter space where you have the DNS. And then once you have the laws and you have your parameters, you know which ones they are, you then compute the actual parameters for the star, which would, in that case, in here, place it, and you calculate the boundaries of the region for around the star. And in this case, for my picture, it would place my star in the green regime. So I would apply the green flux law. And that would tell me what I should do in the stellar evolution code. Now, the main risk with this approach is that, well, there's two of them. One is that there's a new parameter regime you absolutely could not predict ahead of time that just appears out of nowhere. And that's always a risk. Or there's some slight, you know, your scaling laws are slightly off. And when you extrapolate many orders of magnitude, you get a number that can be off by factors of 10 or 100. So these are the risks of this approach. But it's pretty well established now. So I illustrated this with two parameters, which brings me to the importance of non-dimensional parameters, right? So with two parameters is already hard enough. And typically local conditions within a star, you have tons of parameters. But there's the saving grace is this Buckingham Pi Theorem, which tells you that if you have a set of equations involving a number n of physical variables, then and parameters, then the original equations can be rewritten in terms of a smaller set of n minus k dimensionless parameters, which are constructed from the original variables. So this theorem is a formal mathematical theorem that tells you can always reduce how many parameters you have by going dimensionless. And it further tells you what k is depending on your system. But just to give you an example, in thermohaline convection, right? If you thinking about thermohaline convection in the star, you have 8-dimensional parameters. So the local thermodynamic state and composition, local temperature gradient, local composition gradient, and then the 3 diffusivities. But if you go dimensionless, you can boil it down to 3 parameters that are explicit, and then 1 implicit one, which never matters. So this is really powerful, right? You go from an 8-dimensional parameter space to a 3-dimensional one. So the code instruments that we use are almost always using DNS, so where we solve the exact equations of fluid dynamics with microscopic diffusivities, so not any eddy diffusivity. The standard approach we use is typically either spectral methods or finite difference methods. And yet only approximation really is the choice of numerical integration scheme and resolution both in time and space. So the results have to be highly reproducible. If somebody else does the same problem with a different code, they should get exactly the same result. And the standard codes we use in the field are such, and there's many others, but Pencil Code, Daedalus, Snoopy, PADI, and these are often available. So for the verification and validation, I classified into 3 levels. Level 0 is what I just said, right? The same experiments reproduced by other groups should give exactly the same result. If the instability is truly local, a level 1 test is that if you do a similar experiment with a different forcing that is large scale compared with your instability, then if you have the same local conditions, the result should be the same. So for example, if I force my shear using a shearing box or a body force, the result should be the same for the turbulence that ensues. And then the level 2 one is very hard and is basically as computer power increases, the simulations should be redone at more extreme input parameters to try and test the model at these more extreme parameters and avoid stuff like that, right? So that will, but that's that's only time will tell. We need better computers to do that. So in terms of, to finish up, I just want to say, you know, what do stellar observers and modelers want to know from us 3D modelers who have this local approach? I'd be very interested in.
Your time is up, Pascale.
And I'm done.
Oh, perfect. Thank you very much. Okay, thanks for those introductory talks. Just to review, 7 topics. 1, what research questions do we focus on in terms of the panelists? 2, open questions 3D models can possibly answer. 3, 3D simulation approaches. 4, code instruments. 5, dimensionless numbers and why they matter, or maybe they don't. 6, verification and validation. 7, interaction with 1D modelers and observers. So we're going to take a quick 5-minute break where you're going to be working. You have to discuss with your colleagues around you some of these topics. And then after 5 minutes, I'm going to come around and ask you what you discussed. For the Zoom participants, we're going to put you on in a breakout room, and so you can discuss among yourselves as well. Okay, see everyone's soon. There's a question? Yeah, we're putting it up. There we go. Okay, thanks. Okay, everyone, let's try to wrap things up. Bring it back to the group so that we can kind of have some whole group discussions about what you've been discussing the past few minutes. I do want to say that I'm very happy to see people kind of circled up. The room before felt very sterile, and now it feels like we're really doing something. So I think that's very exciting. So as I said, I'm going to kind of just call on some different groups and ask them what they discussed. So I think I'm going to start over here. Yeah, go for it.
I can discuss my problem. Yeah. You want to start with your problem and then I can discuss it.
Okay. Timothy van Reet, KU Leuven. So we basically discussed more along the 7 topics on how they related to our own research fields. So in my case specifically, at least, that would be more. So I'm more interested in the G-mode pulsations in the main sequence. So those are intermediate mass stars with a convective core. And the G-modes are more sensitive to the properties of the near-core region, and you can actually trace the properties of the convective core boundary with that. So in relation to the 7 topics, the relevant questions would then actually be, okay, what is the behavior of the convective core in terms of all the different mixing processes that have been discussed already at various points. So entrainment, convective penetration, overshoot, and so on. And also in terms of the dimensionless numbers, the Rossby number is sensitive to the convective behavior in a rotating star. And that actually also relates to the stiffness of the convective core boundary, and that then relates to internal gravity waves. So that would, for me, be a very interesting topic to explore further in terms of the 3D simulations, to see whether we can link that to the observations.
Great, thanks. We only have time for a few comments by a couple of the groups, so I'll move on. Would someone here like to say something that they were discussing?
Hello, everyone. Yes. So we talk about 7 questions. Oh, I'm Benny. Hi, everyone. So yeah, we talk about 7 questions, and there's a lot to talk about in a few minutes. So I think the most important question we talk about, I think, is about what 3D models can do to enlighten our work. And I think the most important two are simulating convection and mixing, as we hear a lot about in the conference. And because intrinsically, both convection and mixing, they are intrinsically highly 3D, and then without that, we can't really capture the physics. And in terms of comparison, code validation, and verification, I think maybe we can focus more on the disagreement between codes. if everything is like matching perfectly, then we can't really isolate out the key physical parameters that are different between the code, or we should address. And yeah. Any more addition?
That's great. Thanks, Benny.
Just briefly repeat what your most important, was it convection, core convection, or what was the most important science goal in your group?
Convection flows and mixing. Thank you.
Okay, thanks. I'm going to come over here. Would you like to describe your group discussion?
No.
That's the wrong answer.
I guess one topic this is Jim Fuller. We discussed MHD and Dynamo simulations and what kind of geometry you should look at. And of course, it depends on the problem you want to answer. So Jen cares about magnetic braking. So don't trust box simulations. If you care about smaller scale fields, maybe you can trust box simulations. Anybody else want to add?
Okay, going around. Would you like to describe some of your group discussions?
Sure. Okay, so yes, this is Joel Ong from Yale. And I think the one thing we can basically all agree on is we want to get a better handle on how to turn these 3D simulations into science, basically. Like, you know, like, yeah, I quote this verbatim.
Can you define science?
Yeah, okay. So for instance, what properties of the 3D convection simulations we should use to map to other more traditional one-dimensional prescriptions like alpha MLT, or back reactions between the convection that we get in these simulations and pulsations that we also should be seeing in the time domain, or more broadly, what properties of these papers on 3D simulations we should look out for in order to assess the quality as non-experts.
Thanks.
Can I just inject here? I'm trying to paraphrase what these groups say. You all have access, and I'm writing that into the Google Doc. You all have access, and if I'm writing something that you didn't say, please go there with your laptop and edit and improve it or change it.
Okay, maybe could someone, would you mind describing some of your group?
Hi, I'm Bindesh Tripathi from UW-Madison. We discussed mostly about whether we should keep explicit dissipation or we should rely on numerical dissipation, and we had good discussion, and maybe in the interest of exploring extreme parameter regimes, one could rely on the numerical dissipation, but whether the results would be trustworthy or not, that's a different question. So maybe people could keep exploring from two different avenues and try to see new findings.
Great, thanks. There was another big group here, so I want to get your thoughts as well.
So we had some discussion. I'm Janos Stibre. We had some discussion about the importance of looking for convergence. The MRI in shearing box simulations offers a cautionary tale there. We also talked about some important science goals in connecting convection to waves being launched and how that proceeds in future. Anything else? We talked a little bit about interest in moving forward with MHD simulations.
Great, thanks. There were a few other groups, but I think in the interest of time, maybe we can get back to the panel unless there's any other dying, very crucial things that people want to add. If not, I would say that the thing that I've heard the most is, I think, question number 7, which is the connection to 1D modeling. Yeah, I guess would someone like to, on the panel, like to kind of delve into that in a bit greater depth?
Pascale, would you be willing to tell them what you were telling me in Falk about asymptotic models versus empirically calibrated models for going to 1D? You had a really good way of phrasing this when we were talking in our groups.
I do not remember. I do want to say something to that effect, though. Adding small-scale instabilities to 1D models is very easy because everything only depends on the local conditions in the star. And that's exactly what MESA or other stellar evolution codes love to do. Give me local conditions, out pops diffusion coefficient, right? Dealing with convection, which is a very large-scale instability, is much harder. And whether it's even well modeled by diffusion coefficient, that's a big question, and probably not. So that's all I wanted to say, because that's all I really know about these small-scale instabilities. So there isn't a difficulty. The only difficulty is to trust the model. But for the rest, I'll leave it to my co-panelists.
I'm going to paraphrase what I remember Pascale saying to me in Falk when we were visiting on Thursday and over the weekend, which is the thing it struck with me. If you do a whole bunch of 3D models, right, to like test some idea, you have two different ways you could try and incorporate this into a 1D model. One option is you take your 3D models as a set of empirical experiments and you fit an empirical model to that data set that you then extrapolate to your 1D model. You say, we varied Rossby number and we varied some other parameter, and so I'm going to fit some, polynomial function in Rossby number and other parameter that's going to make me a lookup table, basically, that I can incorporate into MESA, and then off to the races with that as your data set. That's one approach. The other approach is that you develop a theory, an asymptotic model. You test that theory against your set of 3D models, and if the asymptotic model survives that testing, then you incorporate that asymptotic model into your stellar structure model or other things. These are super distinct. They sound similar, right? But one is basically just numerical observations and synthesizing that into a convenient way for ingestion, and the other is sort of hypothesis testing. Using the 3D models really as your lab experiment to hypothesis test something that you then extend into another regime. And these are two very different ways of proceeding.
Gemma Theders, what fraction of the time would you say you're in one of those regimes versus the other one? Like when I'm looking at papers, are you usually in that empirical regime where you've just fit a relationship, or are you usually in that asymptotic or analytical theory place?
I'm grinning widely under my mask right now. Pascale? I think different people are in different regimes at different times. So I think Pascale's in the regime 2, test asymptotic models against simulations, right?
Whenever we can, but sometimes we can't, right? I mean, I would say for fingering convection in the hydro limit, we have a pretty good sense of what's going on. But as Adrian described this morning, when you add magnetic fields, we don't. For semi-convection, we have an empirical model we don't understand. For GSF, I think Adrian Barker has a very nice theory with asymptotics that works very well. For shear instabilities, I presented a couple of weeks ago. I believe that we have a good model that can be that has asymptotic scaling that can be trusted. Yeah, we do our best.
Pascale, this is Daniel. I just have a quick clarifying question. I think 3-letter acronyms are dangerous. Maybe not everyone here knows what GSF is. Can you mention that quickly?
The GSF
come up a couple times.
The GSF is the Goldreich-Schubert-Fricker instability, which is analogous to the double diffusive fingering instability. where temperature is stabilizing, but the angular momentum gradient is destabilizing. So it's a centrifugal thermal instability that is double diffusive in nature. And it's pretty important in stars.
I think in contrast, in the Dynamo community, we've often been in category 1 of we have no real asymptotic theory. We just have a lot of observations. A colleague once asked me if I was a numerical observer, and I thought that was a very good characterization for I was at that time in my life. So I think there's a lot of that on Dynamo problems because we don't have a good descriptor. We have some ideas that are tested, alpha, omega dynamos, things like that, but they're.
Yeah, so if I can weigh in on the question of 3D to 1D, how to do that, I think it's understood. Now we are clear. What Pascale is doing is she relies on a macroscopic flow that she can calculate. But assuming a certain macroscopic flow, then there is sort of subgrid scale responses of the stellar plasma, and that is something that Pascale's box and the star approach can certifiably calculate, but she has to rely on the global flow morphology. And so the equilibrium global flow morphology is something that Ben has explained. Our thoughts towards how to go from 3D to 1D are then sort of maybe in certain ways even closer, I think, to what we do in cell evolution. In those phases where it works, and main sequence, massive star main sequence may be a case where ultimately it will work, in the sense that when you do something where you can maybe approach your thermal equilibrium state through some smart coupling of 1D and 3D alternate or co-processing, something that Paul and I have been discussing under the framework of autocorrective modeling. We have a 1D model that we evolve, and then that's a sort of a vision. It's not in place yet, but you could imagine a 1D state that you evolve, that it is fed information from the 3D state so that it knows where it should be going, and so you evolve it, you accelerate the convergence towards the thermal equilibrium state. And once you have reached that in 3D, you are solving essentially the same equations as in 1D, except you do it in 3D. You have the same nuclear physics, opacities, in sort of you still have to sort of do a small amount of boost factor. Your convective velocities may be off by a factor of 5 or 10 even, and there is issues with the scaling, the difference in scaling of wave amplitudes and convective amplitudes. But in principle, then you have something that should be looking pretty similar than your 1D MESA model, except in 3D. And that is sort of then, I would consider like a numerical experiment against which one could validate 1D approaches and improve these models that we have for 1D. We would know what we think really is a 3D correct answer for this particular situation. And so that's one way how we can go from 3D to 1D.
Adam Germain here. I don't want to speak for all the other MESA developers, but from my experience with MESA, we really prefer when there's a theory that we can both understand and have some faith in asymptotic scalings. We've gotten burned a lot in the past with trusting fits way beyond where there was underlying data, both on equation of state, opacity, reaction rates. It's just a really messy business unless you understand what's going on.
Hi, Vicky Antochi here. May I expand the question from 3D to 1D to 3D to observations? So my question is, I think, how far are you from predicting something that we can actually observe? And at the same time, what can we observe for you to be able to validate your models?
Sorry, before you answer that, I just want to chime in that there was a question in the Google Doc by Jamie that I think is very similar, so I just want to pose that as well. Yeah, so what do you consider a great success story for 3D modeling where you make a prediction or explained an observation that improved our understanding of stellar physics, analogous to, say, like the solar neutrino problem for 1D modeling?
Well, I mean, I would say that if you go back, sometimes you have to go back a little bit more to really see the progress. And I think that if I just, 25 years ago, I was working on my PhD thesis trying to just imagine, how does core convection look like? How does shell convection look like? And so I mean, I think you would go to a conference and people would have not a lot of confidence that they can imagine even, like, how does it look like? So now we have simulations that really give us an idea of even what the flow morphologies look like. Like for core convection, that sort of the flow is just going right through the center. There is not any plumes that are rising from the middle and return to the middle. This is not how the flow morphology looks like. So I think this is fundamental. This is fundamental progress in many areas. But a specific example, I would say, for example, 3D simulations have found out that in the late phases, something that Carl Fields, for example, in the back is working on. We have been working on that as well a bit. If you just take convection in the very late stages of the evolution of massive stars, there is global instabilities that are invoked by convective processes that fundamentally help affect the explodability of supernova, and is now believed that this is one of the key aspects of a successful explosion in 3D. And so without an successful explosion in 3D, there's a lot of things that don't work. So this is one example where 3D hydro has sort of discovered new effects that really explain observations. And with the internal gravity waves, I think we're still we're not converging, but I can really see that we will be, if we meet at the next meeting or the meeting thereafter, people will have converged maybe on the interpretation of some observations related to internal gravity waves in massive stars, for example.
Ben or Pascal? Yeah, go ahead, Pascal.
Maybe I can say a little bit. I sort of view the field of 3D hydro for stellar interiors a little bit like nuclear reactions were exactly 100 years ago for stellar astrophysics, in the sense that at the time they had an idea that it was probably that, but they couldn't figure out what were the right reactions to explain the observations. They were missing fundamental stuff like quantum mechanics and electron shielding and all of these effects that turn out to be really important. And Eddington was very good at coming up with these paradoxes, right? Saying, if we really think that, then this should happen, but we shouldn't observe stars like that, and yet they existed. The point being that you need to come up with a very, very simple system in which these theories can really be tested. In my view, the stars are complex for two reasons. One is they have convective regions and stably stratified regions where lots of different processes happen. They rotate and they have a history. And in that history, they can change from having been fully convective to being not fully convective to others. So if we could find really simple stars that have had a really simple history, that were either fully convective throughout or fully radiative throughout, then maybe we can start testing fluid dynamics a little bit better. And I'm sure that's kind of boring for observers. But these are the ones that we need, I think.
So I agree really strongly with what Pascale just said. I think the fully convective stars are a spot where there could be real advances in, I think advances in observations of fully convective stars could lead to real advances in theories and in 3D models. For the question of when have we had a great success, I'll briefly recap a story I told in the talk I gave in the larger program, which was in the mid-2000s in the solar dynamo community. We had qualitative and quantitative agreement with the interior differential rotation profile of the sun, where like even the details are coming in just beautifully, and they're guided by pretty clear theories about coupling to the tachycline and all sorts of other stuff. It was really beautiful. But then a little bit like in Pascale's talk, we wandered a little further in the parameter space. Really, we didn't know how our parameters controlled the simulation, and we stepped into a new regime, and the whole thing just fell apart. The really neat thing out of that is that it's caused a lot of deep rethinking about what the structure of convection in the deep interior of the sun looks like. And there's some thoughts that the sun is actually a rapidly rotating star, and that the interior might be under very different conditions than we had thought. I think the sun offers a lot of real warning, right? 3D simulations are not good enough to reproduce the star we live around and see in detail. And the sun's in some ways a fairly simple star. And maybe we see it in too much detail. It has this real problem that there's an interior boundary layer between the radiative zone and the convection zone that no one really knows the role of or what to do with. And there's a lot of complexity there, both magnetically and thermodynamically and in all sorts of ways. I think we can do a lot better. I think where things get interesting and trustworthy with 3D simulations is when you consider populations of stars or a group of stars over a range of some physical parameter like rotation rate. I think there's a real chance that 3D simulations and observations that there may be some offset that can be brought together where the qualitative behavior is similar, and you can try and understand the origins of the offset. For some of the things that we need to know, we need the things that are really hard to observe. So we need the first thing that comes out of a rotating convection spherical simulation is the global scale flows, things like differential rotation. That's the first time we knew we were wrong with the sun, was when the differential rotation started going the wrong way. And so if we could get sort of a large scale understanding of the properties of differential rotation in fully convective stars, that would be huge. Right? Then you could actually say, do simulations reproduce this class of behavior in these very simple objects? Now, I've just picked for you the dimmest, hardest to observe objects, and I've asked you to make one of the most difficult measurements, which is not just their rotation, but their differential rotation, right? So there's like, what's easy one way may be impossible in another. Field morphologies, maybe also, like if you see repeated, like if all fully convective stars at a particular Rossby number have a characteristic field morphology that you see, and that changes with Rossby number across those stars in the real world, then you could test that kind of idea. That again, that's hard, right? So figuring out how to bring things together is challenging.
I think, Jamie, what you're doing with your question is you're putting your finger at a very good spot, which is that it is, and I like Pascale's comparison to nuclear astrophysics. I think that with the stellar hydrodynamic simulations, there is a tendency, there is such a rich science that we see in the simulation, we get fascinated by it. And so I think Paul and I are guilty of that. We're sort of getting deeper and deeper into things where it's not, where it's very, 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 very interesting, but probably not to many of you. And so I will just say that sort of pointing that out and asking what is it, how does it matter to us is really important. I will just say that, for example, in Jones et al. 2017, we did fit our observed boundary mixing to an F overshooting value, together with a prescription how to sort of treat the MLT towards the boundary, and that could be used specifically in MESA. These are knobs that are existing in MESA. So that is an example, and people could try it and test it. Does it violate something? So I think that's a really important point. In my bullets about verification and validation, I had a point in there that said, it's really important that whatever we do, we're able to verify or falsify. That sort of, and that means comparing with the data. It's the only way how you can validate. If you don't know whether what you're doing is verification or validation, ask yourself, is data, observational data involved? If not, it's verification. If yes, it's validation. And it's a question of, in a sense, for those of us who are doing simulations, how much time should we spend on simulations and theory that can't be validated and falsified? But that's true for 3D simulations as well as 1D simulations, right? If we can't falsify and verify, how much time should we spend on it? I would argue that just as with observations, there are discovery observations, right? And I think there should be room for discovery simulations and for discovery theory. But then there is also Occam's razor, which dictates that if there's two things that you can explain with two different one thing that you can explain with two different theories, you should prefer the more simple one, right? And so, but I think keeping a focus on how our 3D matters to the broader field is really a very, very, very good point. I agree with that. Yes.
Okay, if there's no other thoughts on that specifically, we have about 15 minutes left. I want to say that the last 5 minutes I want to reserve to have the three panelists give some closing thoughts on this discussion. But between now and then, I just wanted to pose a question to panelists and the audience of what are some things we can do as a community to make sure that we're going to make progress and be able to, 10 years from now, have figured out more things than we know right now. Go ahead, Pascale.
I think, again, with this analogy with what happened in nuclear astrophysics 100 years ago, much of the progress was made by this painstaking work of figuring out nuclear reaction rate, which must have been the most boring thing ever. But it's really the way they made progress in stellar astrophysics. And here, I think the way that we can make progress as a community is do the boring work of figuring out transport by small-scale turbulence to start with, because that one can be done. And so I invite a bunch of people who are interested in doing 3D simulations. It's not that difficult. You can all take a code like Snoopy and start doing them. And then, once you really figured out this easy stuff, that you've chipped away at the problem, and you can then focus on the harder ones and get better understanding of the harder ones. Because it's not flashy like, colliding binaries and other things, people don't do it, but it doesn't mean it's not useful, and it's the way that real progress will be made, I think.
Ben or Falk? Oh, actually, first, let's have audience participation.
Do I still count as audience? Jamie Tyre. So I was really interested in what you said, Ben, of, we want to look at the small stars and we want to look at, differential rotation. Because when we have questions like that, like if it is very clear that's something you want us to look at, that's all doable. Like, it's not impossible. It's hard. You got to write some telescope proposals, but a lot of those questions are answerable. And I don't think on the observations and the 1D side, I have a great sense of what things you would love to have that you don't have. And I don't know how to encourage that communication, but if there are things you need or things you want, the more that can be clear on the other side of the aisle, the more we can give those things to you, because I think there is a lot of data that, I don't know about, you don't know about, but
that can exist or does exist.
Following up on that, Jamie, this is Evan Anders. So I've done some work recently with Adam and people. We'll talk about it tomorrow, but basically he came to me, a 3D simulator, and he's a 1D modeler, and was like, hey, there's this like setup in stars that kind of looks like this in terms of like basic simulation profiles, and here's why it's interesting. And I was like, I wonder how we could like set up a simple model of that in a simulation. So I view basically MESA models as a bunch of like background input states for simulations. And if you can like hone in on an interesting section of one of those and like an instability that's there or like a mystery that's there, and there's like a 2 or 3 layer thing or like a simple model we could set up, we as 3D modelers are thrilled and happy to talk to you, because part of the thing is we just don't know what all the mysteries are. And so if there's something that you want 3D modelers to solve, just like tell us what that is and show us where it is in MESA models to give us some places to start.
Thanks, Evan. I think that's kind of related to what Pascale mentioned about kind of trying to do the small scale, not as sexy things. Maybe we can make more easy progress.
Yeah, very short and specific answer to your question. I think what we're struggling with, so one is, what was really useful for us was when the astroseismologist, Connie Ertz and Dominic, were saying, look, here's a observational phenomenon that I hadn't even heard about. I mean, the low frequency excess I didn't know about. And they said, well, I mean, is that something that pops up in your simulation? So that's one way. But the other is what we're looking for is if you, from the observation side, if you want to think yourself, like, okay, so these guys are simulating on that, the conversation will go like, you know, what are the observations that I can have cleaned enough where if these guys are comparing their single, like in our case, say let's say single 25 solar mass star, and they get a result, then and they compare it, they don't turn around and someone turns around and says, oh, but that's a binary, that's a stripped star, right? So creating sort of clean samples that, well, yeah, this is probably representing the kind of object that we're actually simulating. And that's a lot of work for us. We don't necessarily have even the expertise and the background knowledge. Like Ilva would say, oh, it could be this, could be that. I mean, I would not know that by just reading all the papers immediately.
I'm going to say something fairly controversial. Well, I probably say lots of things that are controversial. I think a real problem, the boring work is the important work. And we have real problems with that as a community. We have a real attraction to glitter. Like, oh, it's got chemical mixing with multiple reaction networks and radiative transport and MHD and that is usually the wrong spot to answer questions. Like the spot where I think we can reliably answer questions right now are often in some of the places that look very boring, but where we've, computing's come a tremendous distance, even just over the past 20 years that I've been interacting and aware of it. Practically speaking, that means that 3D simulations, you can run 256 cube to 512 cube simulations all day long, more or less. You can do hero calculations at a couple thousand cubed once. And that gives you a real experimental space to test out ideas. But the ideas that you can test reliably in those spaces are usually still in limited areas. And you can't usually test a whole bunch of different physics all at once right now, because we don't understand how the individual physics work, and we can't get enough separation between the physical effects in a given simulation to say like, oh yes, this is a chemical change to opacity changing the radiative transport versus, nope, the Reynolds number was too low. And so it just ignored that thing and just like plowed right through it. So you have to think really hard about how to do the boring experiments. And we also have to think as a community, how do we support those boring experiments? Because good Lord, it is so much easier for me to write a proposal that's like, well, we do Eddington tensor radiative transport in a curved spherical geometry and blah, blah, blah. And then cha-ching, money flows, as opposed to we're going to very carefully test a whole bunch of like very careful Boussin-esque ideas on like global flows to see if they have anything to do with rotational constraint, right? Because the fair reaction from an observer might be, well, it's Boussin-esque. What's that got to do anything with stars? What's your observable prediction, right? And like we have to recognize where the bounds of our knowledge are and what we can actually do to make progress, because otherwise we just make simulations that confuse us more. So, controversial statement done.
Thanks, Ben. We're running low on time, so maybe we could have each panelist try to just maybe mention in 2 minutes what are a couple of key takeaways that they have from this discussion. And I think, Falk, would you be comfortable going first?
I think that I maybe would like use my 45 seconds to just put my finger at one spot where we didn't have too much time to actually discuss, and that is the topic of the code instruments and how we get code instruments that are really allowing us to perform the experiments. And I just think, you know, over the last 10 years have benefited tremendously from collaborating with Paul Woodward over there, who has really dedicated his life to building really good code instruments. And there's other heroic efforts out there who do that as well. But it is not clear what's the incentive structure for young people to start really dedicating their life to this activity. And I will just say that when I, more than 10 years ago, worked for a couple of years or a few years intensely with the MESA effort, for some time, we would just in Victoria put Bill Paxton on every paper that we wrote. And I mean, he just accumulated a lot of papers from that exercise. At some point he said, don't send me these drafts anymore. I'm not going to read them anyways. And he didn't need those rewards. But you know, are we prepared when you're saying, you know, where's the science? When you do these 3D simulations, where's the science, right? You know, I would say if you want to have, not you, but generally speaking, if you have a brilliant science idea that you can maybe test and put in place. Well, you have the idea, you're going to make the plots, you're going to actually write the paper, but you're going to use one of these fantastic code instruments where 2 decades of work have gone into. If you really are honest and ask yourself, what has enabled proportionally in terms of effort this paper, are you prepared to write that paper and put the code builder as a first author? Right? And so that goes a little bit against the grain of how we usually think about the science. Where's the science? And I'm sort of just, in my controversial statement, I'm sort of putting out the idea that we have to look at these efforts in sort of really an honest community-based sense and really look at what are the different contributions. And I'm challenging the view that the only thing that matters is sort of again, in this sort of hero model, the one person at the top of the hierarchy who had sort of the brilliant idea that no one else could have had. I think that's a view that is not conducive to progress in our field. So that's my 45 seconds.
Thanks, Falk. Love the spice. Love the spice. How about we'll do Ben and then finish up with Pascale.
I think one of the most interesting things for me in this panel and prepping for this panel is just seeing how much work it takes even 3 experts in 3D modeling to figure out how to talk about problems in a similar way. And also the conversations that have been generated from other people trying to understand how to interact with the work that we do. Your very good questions about, from the perspective of observers, what are the things that we've succeeded at? What are the predictions? What are those things? And being able to have the conversation of like, look, those might even be the wrong questions to ask, but here are the questions that might be the right ones to ask. And then Jamie's like, hey, some of these things we might actually have data for if they're the kinds of things that you need answered. I think there's a tremendous amount of progress to be made by truly interdisciplinary collaborations between 3D modelers, 1D modelers, observers, but those are also hard. Right? These are not knock off a paper in a couple months kind of things. These are years of investment to figure out how to talk to each other and where the opportunities lie for the combined expertise. Those are also teams that are hard to support, either in a grant writing environment or in departmental hires or other things. So we have to find ways to create and build those teams across institutions. So.
Okay, saving the best for last, Pascale, our fearless Zoom participant. Go for it. Unmute yourself.
I don't want to keep people from lunch. I just want to actually thank you and all the organizers for actually creating a forum where we can get together. I think that's the most useful thing you can possibly do. And the only thing you could do better, or we could do better as a community, is to do this at the school level, because even the discussions on the stellar evolution are pretty high flying for me. You know, I'm lost a lot of the time, and doing it at the really basic level, graduate student level, so that people like me could learn, be a grad student again in stellar evolution. Maybe some of the stellar evolution people could be grad students in fluids. That would be great. Maybe let's think about that.
Great, thanks a lot. So I want to thank the panelists again for a really engaging and interesting discussion. And I think it's time for lunch.